just to recap our objectives in this mini course, our learning goals, so to speak. Yesterday, our goals were just establishing notation for the rest of the course and having a panorama of cryptographic schemes that have been proposed and whose security stem from intractable problems related to coding theory. And today we will address these topics. We will make some security considerations. We will deal with the choice of codes for cryptographic purposes, and also deal with a few implementation issues, and with very briefly with some research problems that we have today. Okay, so I won't have time to make a presentation of everything, all kinds of attacks that have been devised against code-based crypto systems, but a great deal of them are variations on one specific subject, which is how to apply information set decoding to a public key or to a cryptogram to extract information from it. But I can tell you that all those variations have exponential cost. What researchers are trying to do is to reduce the constant in the exponent. The cost remains exponential. So we are quite safe in this regard for code-based cryptography. If a scheme is well implemented, then we have very good reason to be confident that our overall result will be secure. So this is an abstraction of several lines of attack. It does not exhaust the area of how to mount an attack, but it covers a great deal of the literature on the subject. So this is very basic. The important thing here is to grasp the essential concepts. So, what is an information set given a linear T error correcting code specified here by a generator matrix G? Could be specified by a parity check matrix as well, but let's stick to a generator matrix here. Assuming we have a blurry code word C, so it's a code word with some errors. At its most, T bits are in error here. An information set is a set of coordinates on that blurry code word where there is no error. Okay, it's only that. It's a subset of columns, of positions in the blurry code word where there is no error, where the bit corresponds to the underlying code word. Well, of course, we don't know what the error set is, whether a given subset of the coordinates is an information set or not, unless we are able to correct those errors. But we'll try to find one. We'll guess an information set and check if it's really an information set. This guess will be implemented in several possible ways, and how we do that will define what kind of attack we have. So this is important. We know that the blurred code word C is correct in all positions specified by this information set J. Okay, how do we decode given an information set? Assume we have an oracle that knows one information set, a set of positions where we don't have any error. So that will be easy. If the size of the information set is at least equal to the code dimension k. What do we do? Restrict the given blurry code word to the coordinates specified by your information set. Drop everything else and drop the corresponding positions from the generator matrix G. So restrict it to the same positions specified by the information set. The results for the generator matrix will be a k by k matrix. If we are lucky, it is non-singular, so we can invert it. And the important thing is that since we are only considering coordinates where there is no error, actually the relationship between the given code word and the shrunk generator matrix G, there is only this. There is no error term here, it's 0. And if that k by k matrix is invertible, we can recover the linear combination U by multiplying the restriction of C to J by the inverse of that matrix. So if we have the linear combination that produces the underlying code word, we have it, and we can compute the difference to recover the error positions if we like. So as long as we have an information set, we can decode and correct all errors. So the problem is, how do we get an information set? It's hard. Otherwise, the overall general decoding problem or syndrome decoding problem would be trivially solved. Well, assume that we can check if the result of that operation, if this result, if the value of U we have corresponds or not to a proper code word. How do we do that? We would have to compute U, then multiply it by the full G matrix and subtract from the given blurry code word. So in principle we would have the error pattern, and we just count how many one positions we have in that error pattern. If it is up to T, then we have a successful decoding. We have corrected all errors. If we fail, then so sorry, the error pattern we obtain will be random looking in general. So we have to pick a different set J, a different candidate for the information set, and try again. There is not much more to it than that, except for cleverness when we schedule operations, how we do that. So let's assume that we can, in the best case possible here, we can do everything involved in one check in 1 unit of time. It's not very plausible this. We have to try to invert a matrix, then multiply it by C and compute the Hamming weight of the resulting error pattern. But let's assume that we have schedules that involve all operations so that everything is so fast that it fits one machine clock, let's say 1 nanosecond or so. So it's 1 unit of time. Then what is the expected number of attempts we have to perform until we get a successful decoding? So suppose that we have an information set with S positions, S coordinates. Our objective is to get an information set with K coordinates. What is is the probability that when we pick at random, or not quite at random, according to any specified criterion, we pick another coordinate not yet on J. What is the probability that the resulting set is still an information set with one more coordinate? It's roughly 1 minus t divided by n minus s, because the probability, the rough probability that another coordinate not containing an error is proportional to the number of available positions that are not expected to contain error. There are t errors out of n positions overall. So the probability that one particular coordinate has an error is t over n. We have already removed s coordinates that constitute an information set, so all t errors remain on the available n minus s coordinates. So if now we proceed by adding one more position, one more position, one more position, we need the sequence of information sets we get to be an information set to not contain any errors. So the probability when we do this until we get a set J with k different positions will be the product for S vary from 0 to k minus 1 of that expression. And okay, this is an approximation, but anyway, this number is quite large. It's exponentially large in the parameters here. We have to multiply that number, that expression by something quite similar k times. So it's exponential, roughly exponential in k, in the code dimension. And also we have to be lucky enough that the resulting k by k matrix is invertible, but the probability that a random k by k binary matrix is invertible when k is large is approximately this number. It's 3/7 roughly. So the work factor, the amount of steps we are expected to perform, even given a unit cost, I assume that we can do everything we need to solve a linear system, etc., in 1 unit of time. So the overall amount of steps will be given by this expression if we compute this for parameters that appear in the literature, say codes of length 2304 and dimension 1280 with 64-bit error correction capability. Then this is a logarithm to the base 2. It's a binary logarithm. The number of steps, of attempts we are expected to perform until we get a successful decoding is 2 to the 78th. 2 to the 78th is roughly Avogadro's number. It's 1 mole of operations. It's an extremely large number of operations. But still today, this level of security, the adversary would have to perform the same effort as to count all molecules in a glass of water or so. It's considered very low. It's legacy level. We would like this figure to be more like this, close to 128. So if we pick this kind of beautiful combination powers of 2, we get an effort to apply information set decoding very close to another power of 2, 1 to 28. Yes?
In the definition of WF, the parity is smaller than 1, right?
Sorry? What is model donor?
The pi of S from 0 to k minus 1.
This product?
Yeah. Isn't it less than 1? Should that be in there somewhere?
Sorry. Yes, you're correct. You have to invert this. So it's this to the minus 1. So if the probability of success is that, the effort is the inverse of that. Thank you. I'll fix this. But fortunately, it's not failure in reason. It's a missing minus 1 exponent. So, in practice, since we cannot simply assume that we have unit cost, the number of computer clocks will be higher than this, but not that much higher. Techniques to implement this and variations to obtain an earlier board, we can early on detect that one candidate for an information set is wrong. We can simply drop it and pick a different one. This is the kind of research work that is being conducted regarding how to attack code-based crypto systems. So in practice, we will have something slightly larger than this, not much larger. So it's reasonable. It's not far from reality if we simply assume that we can do everything in one unit of time. If we have a really good, a really clever implementation of that, and if we can put everything in hardware, for instance, then it's much more reasonable to assume that the number of steps will be close to that number there. So we already have a very rough guideline to what the actual parameters will look like, assuming that we don't use a code that has any kind of vulnerability, any kind of internal structure that an attack could use to find a shortcut to extract more information quicker than doing this. Okay? So here it's only a recap of that. In the literature, we find dynamic programming techniques, and sometimes it's simply cleverness. So this operation can be done faster if you do that first. So that's it. Okay. So there are several other attacks, other lines of attack, families of attacks. This is the overall principle that we find in a large number of attack attempts, but there are others. For instance, there is an unbalance, an interesting unbalance between the costs we find for attacks whose objective, whose goal is to recover one message from a given ciphertext. So the adversary's goal is to decode only one message, not all messages, all possible messages, only one message. Is content with decoding only that one. So it's kind of intuitive that the cost of this kind of attack is not the same as an attack that tries to discover what the private key is. So we would be able to decode anything at all. And indeed, the unbalance is sometimes enormous. If we try to decode one message using information set, it's possible that the cost is 2 to the 128. And if we try any attack whose purpose is to recover the key, the cost will rise to 2 to the 600 or 700. So it's much, much, much larger. Actually, this can be viewed from a different point of view. It's an opportunity to introduce more symmetries to your code so that the cost of message recovery remains the same. The cost of key recovery drops not below the cost of message recovery. So the bottleneck is message recovery. We can reduce the cost of key recovery as a trade-off to obtain a more efficient implementation, a more efficient set of parameters. So, for instance, the public key for both MacLease and Niederreiter is a matrix. So it's a large amount of data. It's a quadratic amount of bits. If we can obtain a public key that is say a series of circulant matrices or dyadic matrices, we only need to store and keep and use for processing the first row or a G or H matrix. So the space complexity drops from quadratic to linear, and algorithm complexity can also be reduced from cubic or quadratic to subquadratic to something like n log n, n log square n, according to the system. If the resulting cost of key recovery remains of the order of message recovery, we are not reducing the overall security of our system. We are only pushing back one point where security was an exaggeration to the same point where we find our bottleneck, and at the same time we're improving the usability and practice of our system. There is a different line of attack. Actually, it's related to this. How do we find the private key? One possibility is to try to find low-weight code words in the dual code. Given a code, we try to attack the dual code instead. If we can find low-weight code words, we'll see today, we'll see in a few minutes, how this could be used to decode. So it's actually one occasion where key recovery can be more efficient than message recovery if we don't choose a suitable code, a secure code. There is also the possibility of exploiting the very underlying algebraic structure, not specifically the external one, the fact that the public key is one element of one particular subring of the ring of all matrices. But if we choose an algebraic code to be the basis of our crypto system, it's possible, according to what we chose, that we can map the problem of recovering the trapdoor to some completely unrelated or seemingly unrelated computational problem, like solving systems of nonlinear equations, multivariate quadratic equations. It's a popular choice for an attack to mount an attack, just to use Globina basis techniques. So instead of decoding, we try to solve a nonlinear system. If we are successful, then we can map back and obtain the trapdoor. But again, if we choose our code properly, none of these attacks has sub-exponential complexity, so we are safe. If we're not safe, if for a particular choice of code, any of these attacks has sub-exponential complexity, or even worse, polynomial complexity, then we simply drop that whole family of codes. They are not secure. We stick to codes that have withstood scrutiny and attack attempts. sometimes exploiting symmetries can lead to improvements, but not by much. Say, if we are trying to apply an attack that finds a low-weight code word in the dual code, if we know that the matrices are circulant, we don't have to apply the attack again and again to recover row by row. We find a single row and we just rotate it, and we have already a basis for the dual code. So the attack complexity would be reduced by a factor of k, but it's polynomial in the code dimension. It's linear in the code dimension. It's not an exponential speed up. It's only a polynomial speed up. So we just increase our parameters by log of k or log of n. It's a very small increase, and we are safe again. There's no real problem in adopting codes with this kind of symmetry. They don't contribute that much to attacks. Okay? Okay, we also have a type of attack that has nothing to do with the nature of the code, the nature of the decoding process, but just how we implement it. If our decoder runs slower or takes more energy or anything like that, when one particular bit, the private key, is 1, then when it is 0, then in practice in principle at least we could measure that. We can measure how much energy is being spent or how long the process is taking, and we can infer information about the private key that can allow us to recover it. But anyway, this is related to how we implement our algorithms. There are alternatives. Always we can, at the cost of making it slightly slower on average, we can make all operations take the same time, spend the same amount of energy, and so on. But we have to be careful in practice, especially on some platforms that are particularly vulnerable. Say a smart card whose power source is external, so it's easy to measure how much energy it's spending. We have to be very careful about how we implement things here as well. Not only how what family of codes we choose, but how we manipulate them as well. Okay, so next of the 4 overall subjects we will address in our second part, how do we choose the code? I must tell you, yes?
Discussing about message recovery, but that's any general message. If I want to focus on one specific message, I don't care about the rest of the communication, but in the middle, if somebody sends an alarm signal or something, I just want to detect that specific message. So can we even bring the complexity even lower than the normal message?
You mean if you know something about the message already? No.
No. It's like, I know, like...
So you wanted to distinguish between a generic message,
And
could be spam or so, and something really important from the point of view of the attacker?
For example, I know that like he can send any messages to the email or whatever, but there is a specific kind of email that will be an alarm. And I just want to detect when he sends that message and go there. So will it be even less than the normal message?
No. The answer is no. The best attacks we have when our purpose is only to distinguish one particular message from a generic message. All known attacks will work with the same complexity when we have one particular message or any other one. When you encode using codes, unless you do something completely off, completely wrong, you don't choose your code well, your implementation is buggy or so, what you obtain is a set of cryptograms indistinguishable from random. So whether it is a very special message, a very special plain text message that is encrypted there, or it could be even a set of random bits, you would not have enough information I mean, above the specified security level. So if the level is 128, the effort to distinguish them would be of the order 2 to the 128 as well. So the effort of merely distinguishing between one particular code word and random sequence of bits is exactly of the same order of decoding for what we really use in practice, the same order of recovering the trapdoor. There is no known way, if you choose code properly, of distinguishing between two messages. And actually, this is what we really need for cryptography. The modern notion of security is not that the attacker wants everything. I will not be satisfied until I get the whole message. No, the attacker we have to protect it against is one that will be satisfied if he can merely distinguish, recover one bit of information about your message. This concept is called, in its most stringent form, indistinguishability against adaptively chosen ciphertexts. So you give a lot of power to your attacker, and even so, he cannot attack your system. For codes, for properly chosen codes, for the families of codes we know that there is no known vulnerability. The best way to solve this is the same as doing everything. So there is no difference between merely distinguishing a code word from random and recovering the decoding trapdoor. Okay? So how do we choose the code? Well, this is not exactly witchcraft, but it comes close to. Because actually what we do is check for structural vulnerabilities, try to apply some modification of existing attacks, but there is no methodology to create a family of secure codes. So we apply everything we know regarding vulnerabilities, and what we get in practice is that actually we don't have too many choices left. Most of the codes we know are vulnerable to one kind of attack or another. There are a few that have withstood cryptanalysis for decades, and as the knowledge of this kind of thing progresses, we sometimes get a firmer grasp of why that happens. In other cases, it's not exactly the same thing. But okay, so let's see what we do have in terms of choosing the code. So, what happened here? Okay. So, not all codes are suitable. In the literature, we find perhaps a dozen families of codes that have been proposed. Sometimes the family was refined after an attack, and then the result was attacked again and again until it was finally discarded completely. For instance, read mirror codes have been proposed and broken. generalized Reed-Solomon codes have been proposed by Niederheide together with this crypto system. He proposed to adopt GRS codes, and his proposal was broken as well. Gabby-Julian codes have been proposed and broken. There is a large cemetery of proposals in the literature, actually. But there are a few proposals that, surprisingly, seem to be resistant against almost anything. And foremost among them is the family of Gopper codes. Gopper codes were proposed in 1970, so it's 45 years ago. People have tried to break them. They seem to be okay, except for a few subfamilies. Purely binary Gopper codes, if we base them on a binary polynomial, we have a quick look on this. So there are a few weak codes in that family, but we can very easily avoid them. We know from a very recent work that we can distinguish a Gopper code from a random code by merely looking at a public generator matrix or parity check matrix. The cost for doing this is essentially quadratic, so it's very efficient. But distinguishing a code from random can be bad news for security proofs, not for crypto system itself. So we can look at a generator matrix and be sure this is a Gopper code. Okay, how do we decode it? I don't know. I have no idea because I don't have the decoding trapdoor. It's not very much that we lose here. Still, Gopper codes are by and large secure and very popular and very efficient. They are not the best codes we know. We'll see why. Sorry. But let's have a quick look. I presume that most of you know what a Gopper code is, so I apologize for that. But it's also possible that many of you don't know what it's all about. Let's have a very quick look. Gopper code is defined by one polynomial defined over a finite field of characteristic 2. So the coefficients will be taken from f sub 2 to the m for some given m. And it's also defined by what is called the support. A Gopper code is a subfield subcode of a GRS code. So notation here is reminiscent of what we find when studying generalized Reed-Solomon codes, because they are a subfamily of generalized Reed-Solomon codes. And surprisingly, although if we pick a random GRS code, we can usually attack a crypto system. If we restrict ourselves to Gopper codes, we can't break them. It's a strong subfamily of GRS codes. Okay, so given one monic polynomial, it's not necessary that it is irreducible. It's a popular choice that G is irreducible, but it's not necessary, and sometimes it may be advantageous to pick a composite polynomial here. But let's assume for the time being that G is irreducible. So what do we observe regarding Gopper codes? Oh, sorry. There is one restriction. None of the n elements of the support, n will be the code length, must be a root of the polynomial G. If G is irreducible, then automatically the support will be disjoint from the roots of G will be an extension of f sub 2 to the m. So they are very easy to generate. Just pick a polynomial, pick a set of random elements from that finite field of characteristic 2. It's not necessary that the characteristic be 2 here, but since from yesterday we decided to focus our presentation on binary codes, so let's stick to that same convention here. So, given a polynomial G and a support L, we already have a GOPA code. So, they're easy to generate, quite plentiful. How many polynomials do we have? How many possible supports do we have? An enormous amount. Some choices are equivalent to others, but still the number of distinct GOPA codes is enormous. And they are quite random looking, because, well, essentially we are picking this at random. When we look at the available generator matrices and parity check matrices, they do look random. They are almost indistinguishable from random. It took 43 years for someone to devise a way of distinguishing between GOPA code and a completely random code. And they are actually quite efficient. The error correction capability is very high. Well, we need to define a syndrome function. It has this form given, where is it? Here. Given a word C, an element of our vector space restricted to the base field f sub 2. Because we will deal with a subfield. The subfield here will be the base field f sub 2. So given a random element from this vector space, we define its syndrome to be this polynomial mod G. It's C sub I times the inverse of this polynomial x minus the corresponding element from the support. The inverse is computed mod G. If G is irreducible, then we can always compute this inverse. If G is composite, it's possible that we cannot even define a syndrome function, but if we restrict our choice of G and our choice of the support, we can always impose the restriction that L sub I is not a root of G, then we will be able to invert that polynomial mod G. This function is clearly linear in C sub I. We are just multiplying by the weight and adding everything. So that's fine. Finally, the GOPA code, gamma of L, the support, and G, the GOPA polynomial, is the kernel of this syndrome function. Simple as that. The distance of a GOPA code is known to be, in general, at least t plus 1, where t is the degree of the GOPA polynomial G. In the binary case, you can do more. In characteristic 2 and restricting the code words to those defined over f sub 2, we know that the minimum distance is at least 2t plus 1. So in principle, we would be able to correct uniquely up to t errors. The distance may be larger than that, but we have this as a theorem. GOPA himself was awarded the ACM thesis award in 1970 because of this result. So it was a quite surprising result here. I was told it was called the GOPA miracle at that time. So we can correct twice as many errors as we would be able to do in general, as compared to alternate codes or so. It's a good family of codes. He was awarded the ACM Thesis Award. So how do we correct errors? How do we decode COPPA code? Very quickly, we have to construct an error locator polynomial, which is defined as this. It's the product of factors of form x minus an element of support for all positions where there is an error. So if we have this polynomial sigma, and we are interested in knowing if one particular position, if the ith position has an error or not, we feed the polynomial the support for position I. If it is 0, we know there is an error at that position. And how do we correct it? Just flip that bit. So, how do we compute this polynomial? Kind of chicken and egg problem. We don't know where the errors are, so we don't know what the error locator polynomial is either. Except that we can build an equation that sigma satisfies, and then we solve that equation, we get sigma, and we can locate the errors and fix them. So the key equation is an equation that sigma satisfies. It is based on this observation. We can write the polynomial sigma as the product of factors x minus L sub I to the E sub I. E sub I is 0 or 1. If it is 0, this factor is 1. It doesn't contribute. If it is 1, then we have that factor. So now let's abstract that polynomial and compute its derivative, its formal derivative with respect to x. After some manipulation, we get this interesting expression. If it weren't for the presence of sigma of x here, this expression is very similar to the syndrome function. If we compute this mod g, we would have essentially the syndrome. And this is exactly we have. The derivative of sigma of x is sigma of x times the syndrome function applied to the error pattern E mod g. Okay, so do we have to solve a differential equation mod g now? No. Let's be clever. Let's not solve a differential equation. Let's see what else we can extract from the key equation that. Well, this is a summary of how we correct errors. So we have to compute the syndrome, then compute the error locator polynomial, and then fix the errors. Okay. So let's see. We have a given blurry code word. We computed syndrome. The syndrome function is linear, so the syndrome of a received code word with errors equals the syndrome of the error vector. If the syndrome of E is 0, there are no errors, or we are not able to detect any errors there. So we are done, nothing else to do. Otherwise, assuming that G is invertible, G is irreducible, then S of X should be invertible mod G. Let's have a look at 3 properties we have regarding the polynomial sigma here. Since squaring is linear in characteristic 2, we can rearrange the terms of sigma so that it has the form some polynomial A squared. It's the terms of even degree, you can group them together, plus x times another polynomial squared. We group together the terms of odd degree. We take a factor x and what remains is a polynomial of even degree, so we can do the same as we had done for A and apply it for B. Second property is if we derive this, now if we formally derive this, because we are working in characteristic 2, all that remains is this. If we derive this, a factor of 2 appears here, in characteristic 2 it disappears. Now we apply the chain rule here, we'll have x, the derivative is 1 times b squared, which is this, plus x times the derivative of b squared, same thing, a factor of 2 will erase that contribution. So the derivative of sigma is actually only this. And finally, dropping for the moment the mod g, we know that the derivative of sigma is sigma times the syndrome, mod g. Okay. So by combining everything here, we know that b squared is the derivative. It has this form, so we substitute this in there. So it has this form here. It means that there is a relationship between polynomials a and b, mod g. A equals b times some polynomial v, which has this form, is the square root of x plus the inverse of the syndrome. Mod g, we have to invert s mod g, and we have to compute the square root mod g, but that's not a problem, we can do it. And so we end up with an equation of this form. How do we solve this kind of equation? Any hint? Any guess? Any? How? So log? No. How do we compute the inverse of S? What kind of algorithm do we use to compute a modular inverse? Euclid's algorithm. Same thing here. Euclid is used to solve equations of this kind. So we have Euclid's algorithm applied twice here. And so let's rephrase our problem. Solving that equation A equals B times V. V is given because it only depends on the syndrome and the Coppa polynomial G, which if we are the legitimate user, we know G, so we can compute V. We need to solve an equation of this kind. Find A, B, and some polynomial F, so that B times V plus a certain multiple F of G equals, there is an extra condition, because sigma is the square of A plus x times the square of B. The degree of A cannot exceed half the number of errors. The degree of B cannot exceed something potentially slightly smaller. But that's okay, we can impose that condition as well. So we can solve this using the extended Euclidean algorithm. This constitutes Parsons' decoding algorithm. It's his idea. Paper published in 1975, I think. I will not get into details here, but it's quite similar to the algorithm we would use to invert S. The only difference regarding the usual Euclidean algorithm is the halting condition here. We impose that we stop when the degree of G is not larger than half T, because G will play the role of polynomial A, and C, this other variable here will play the role of polynomial B. So in the end we get the error locator polynomial sigma this way. Euclid's algorithm is quite efficient, and it's quite straightforward to implement with the it's here. It's just to implement this, and that's it. So in the end, having the error locator pool, because these errors are binary, you can simply pinpoint where the errors are and fix them. And that's it. As simple as that. That's one of the reasons that copper codes are among the favorites for cryptographers, for code-based cryptographers. Very easy to implement, very simple, yes? Could you please speak a bit louder?
Is there an advantage by using non-binary copper codes?
None is known. I've myself conducted some research about this. It's possible to obtain something similar to Copper's miracle. You can correct more than t/2, but less than t errors when characteristic is not is odd. It was conceivable at that time that you could reduce key size a bit more, but no, you can't. You can improve a text by a factor that is polynomial, but it corresponds to the shrinking factor for your key, so you have to increase them again. So you don't gain anything by resorting to odd characteristic, and actually you lose something if you want to implement this in either software or hardware. Here, if you want to add vectors, you can use an exclusive OR. It's readily available in programming languages and hardware. It's very, but if you choose, say, characteristic 3, no, you don't have readily available instruction or hardware that can do that.
Thus, if the case if you use a non-irreducible polynomial, thus, so maybe you can use the standard Boolean algorithm.
You can do better than this if you choose G to be composite in some ways. A student of mine has done research on that, and we'll see in a moment. But they are not as good as they seemed at first glance. Okay, but we'll see. Okay, so that's it. So having had this quick look at how to handle copper codes, let's have a look at what the results are. Let's use a copper code. Let's pick parameters according to the work factors we are estimating to attack the system. We have a different problem here, which is the key size problem. Suppose we need to satisfy security level of 2 to the 80-bit security level. So we could pick M equal to 11, the code length slightly below 2000, K is about 1400, and introduce 42 errors. Key size here will be 661,000 bits. It's very large. If you want to satisfy the highest practical security level 2 to the 256, then keys get really large, 9 million bits. Again, nobody in its full mental health would choose to use this, although I must tell you that there are people trying to standardize keys as large as this. So it is about 200 kilobytes long. I mean, 200 kilobytes, who cares about this? Nobody will use that. How come you want to standardize this? It will be useless. But anyway, so we do have a problem here. If we pick a random copper code, according to those prescriptions. We have a potential solution, but it's not practical, not really practical. It's too large. Even using a systematic Gopper code, so we don't have to store the identity matrix, or we don't have to multiply by it, but only the essential part of a generator or parity check matrix, a public generator or parity check matrix. It's too large. How do we tackle this problem? So perhaps there are compact Gopper codes, short Gopper codes in some sense. Okay, so just to recap, we need a monic polynomial G and a sequence of L distinct elements. That's the code support. We know that Gopper codes will be interesting for implementation. They can correct a lot of errors. Cryptanalysis has been largely unsuccessful for Gopper codes after 45 years. And so our goal will be to replace the quadratically sized keys by much smaller ones. Is it possible? It's possible when we consider Cauchy matrices. Cauchy matrices are matrices whose elements M sub ij have this form for two sequences Z and L of distinct elements, two disjoint sequences of distinct elements. Cauchy matrices have a lot of interesting problems. They are all non-singular. You can perform arithmetic with Cauchy matrices more efficiently. And there is an interesting property of Gopper codes. It was published by Tsang and Zimmerman in 1975. It's this theorem: any Gopper code whose Gopper polynomial G is square free, it can be composite. You only have to ensure it doesn't have repeated factors, so it's square free. It admits a parity check matrix in Cauchy form. Well, we can see here that a Cauchy matrix has a very short representation. Instead of storing the whole matrix M, we could simply store the sequences Z and L. It should be N here, but T is fine as well. So instead of quadratic storage, we have essentially linear storage. There are problems in choosing Cauchy matrix, parity check or generator matrix for a Gopper code in cryptographic applications. In that the code structure is apparent. We can pick a few elements of the Cauchy matrix and solve linear systems, or actually solving a very simple linear system, and recover Z and L. So that's bad. That has to be addressed. Fortunately, we have ways to hide that structure. But on the other hand, the usual tricks, which is pick that matrix and find its systematic form, it will destroy the Cauchy structure of that matrix. Now, okay. Let's have a look at another family of matrices, the family of dyadic matrices. Let R be a power of 2. A dyadic matrix, H, is an element of the ring of R by R matrices, where the element H sub ij equals to a given vector of length R, vector H, indexed at I exclusive or J. So pick the indices, exclusive or the indices, use the result to select an element from a vector, and we get the corresponding element on the matrix. to have a feeling of what a dyadic matrix looks like. It has a certain symmetry. It's not circulant, but it's composed of some matrices that have the same structure as the matrix as a whole. So essentially what we do here is, for this 2 by 2 block, repeat this element here and this element here. Now pick this 2 by 2 element and the blue element, repeat the red element here, repeat the blue element here. So we are crisscrossing the matrix to get this structure. And dyadic matrices form a proper subring of square matrices. The representation is compact as well. You only have to store the vector h. Arithmetic is very efficient if you apply the fast Walsh-Hadamard transform. It's R log R. Inversion can be done in linear time for binary matrices. Results will be 0 or 1. You just have to add the element of h. If it's 0, it's not invertible. It's 1, it's invertible. You have the determinant. Computer the determinant can be done in linear time as well. So our strategy will be to find a dyadic Cauchy matrix. I will not provide any more details. We have the equations here. This is a theorem in my student's master's thesis. There is a condition that vector h must satisfy so that the resulting dyadic matrix is also a Cauchy matrix. It's this condition. And indices starting from 0, not from 1. And what are the sequences Z and L that define a Cauchy matrix? So Z will be the inverse of H, L will be the inverse of H minus the inverse of 0 here. So it is possible. There is a very large number of dyadic Cauchy matrices in the binary case. You actually can do the same in larger characteristics. You can have not a dyadic but a triadic matrix in characteristic 3, pentadic matrix in characteristic 5, and so on, but there's no advantage in using that. And key generation has almost linear complexity. Encoding, decoding, almost linear complexity as well. We get reasonably short keys, about 12,000 bits for security level 2 to the 80. It's 12,000 instead of 660,000. For a more practical security level, it's less than 2,000 bits. About, I think, 64,000 bits for the top security level instead of 9 million bits. However, security is still under scrutiny. We have to increase key sizes a bit. They remain small, but not as small as we would like them to be. For instance, an RSA key at this security level would be only 1,024 bits long. It's 12 times larger than an RSA key. There is a very recent attack published last year that apparently reduces by a further polynomial factor. It's still polynomial, so it's not in principle a reason to be desperate about security, but our goal here was only to reduce key sizes. We don't reduce them as we would like them to. We would like to. But it's possible to impose some kind of symmetry to obtain shorter keys. And we are still dealing with copper codes, a family of codes that has interesting security properties. Okay. Are there alternatives to GOPA codes? Yes, there is a very recent one. Most other codes have weaknesses. There is this recent trend, which is recent. Actually, it began in the year 2000, and for 12 years, people tried and failed several times, time and again. They tried and failed to base crypto systems on Gallagher codes, on LDPC codes, low density parity check codes, which are codes that admit an extremely sparse parity check matrix. For instance, it's a 10,000 by 20,000 matrix, having only around 3 bits on each column. Surprisingly, such codes that are created randomly. There is no further structure than this. The matrix has to be sparse, and that's it. They have an astoundingly good error correction capability, about 3 times better than a GOPA code with the same dimension here. I don't think I have time to explain in detail how this works, but it's one method to decode Gallagher codes. Here we have the bit flipping technique. It's essentially guess which positions of the received code word are more likely to contain an error because they contribute to a larger number of parity check errors, to positions on the syndrome. So we have here the syndrome with a 1 instead of a 0. If there were no errors, then the syndrome would be 0. If one given position contributes, I think it's the other, no, here. This position on C contributes to parity checks in 3 positions. If one position contributes to a lot of parity errors, parity check errors, then it's highly suspicious. It's far more suspicious than one position that contributes with just a few parity check errors. So bit flipping is essentially this. Guess what positions are more likely to contain an error. Your guess is based on how many parity checks that positions contribute to. Flip those bits. It's binary, so correcting the error would be simply this. If this bit is in error, just flip it. You flip it, you update the syndrome, and you try again. If you're lucky, the number of parity errors on S will decrease and decrease and decrease until it gets to 0. If you're not lucky, you can go into a loop. So sorry. But if you choose your parameters well, you can get a very high probability of correcting all given errors. If we were talking about communications, we would not know in advance how many errors a given received word contains. But we are talking cryptography, so the errors are introduced on purpose. We know beforehand we have T errors. So we can use this knowledge to choose parameters so that the probability of failure is very small. We can filter our generated code, or the code we choose, to decrease the probability of finding a loop condition here. And so what is the result of all this? Okay, let's skip all this. It's called bit flipping. Okay. What we get here is that, well, we can implement this. The algorithm is very simple. The only thing that is not really good here is that it's quite memory consuming and slow. We have to count how many parity checks each position affects. So this position is involved in this number of parity check errors. The other position, another number. Then we find the positions with the largest number of affected parity checks, and we flip them. We, in principle, would have to maintain a counter for each of the n positions on the received word, so it's a linear amount of memory. We can do far better than this. About security. LDPC codes are not really secure. After 12 years, people concluded they are not secure. What if we increase a bit the density? Instead of a very, very small order of one, a constant small number of errors, or sorry, non-zero positions on each column of the parity check matrix. How about increasing that to order of the square root of n? This number is interesting because it's still within reach of Gallagher's decoding techniques, bit flipping and belief propagation, but it's high enough that we cannot find low density code words and the dual code. So we cannot attack the code, but we can still decode it using Gallagher's techniques. So what we have here is not properly low density parity check codes, but moderate density parity check codes. It's low but not that low, high but not that high. It's just a Goldilocks zone for cryptographic applications. So, short keys. We can have quasi-cyclic MDPC codes. It's just a matter of choosing a very sparse cyclic or quasi-cyclic parity check matrix and finding its systematic form, since circulant matrices form a proper subring. The public matrix will still be quasi-cyclic, so we only need to store the first row. The private key is sorry, the private key is sparse, so we can do better. We can only store the positions of the non-zero element. The public key is not sparse. It's dense, but since it's in systematic form, we can drop that part of the parity check matrix and store only this small part of the parity check matrix. The results are amazing. So just to recap, this is what we can achieve with couple codes. This is what we can achieve for the same security levels using quasi-cyclic MDPC codes. So we are getting very close to RSA. Not exactly the same size. We are getting close. Oh, so that means that even QC MDPC codes are worse than RSA. Not exactly, because key size is not the only thing you have to tackle when you are implementing that. So in fact, I argue that RSA, even having shorter public keys, will take more computational resources, which can prevent its use, the use of RSA on many embedded platforms, while QC MDPC codes, although they have somewhat larger keys, will fit your platform perfectly well. So we have a security solution for encryption on certain platforms where RSA is not available because of the resources we need to process. We have to process very large integers. Here, all integers except for one, which is one single counter, not n count. We can make do with one count. Everything has only one bit. So not thousands of bits, but just one bit per integer here. So it's quite competitive with RSA on the Internet of Things and things like that. So this is a summary of how we can implement this on a very constrained platform. It's possible to reduce, as I said, the storage from linear, from n counters to a single counter, not merely order of one, but exactly one counter we can make to a single counter, and performance is good. I have the values here. An implementation written in portable C, no assembly language, of the Niederreiter crypto system. The implementation includes everything. So I've seen papers where only encryption is performed on a microcontroller or so, or a wireless sensor node. No, put everything on your target platform. We conducted experiments on this processor. It's a PIC24F and alphabet soup. Yeah. So the implementation. Okay, no. These are not the results for the implementation. These are the resources available to us. We only have 8 kilobytes of storage for our variables, 32 kilobytes for the program itself. But what is interesting about this microcontroller is that it has a TCP/IP module ready for use, so it's quite characteristic of the Internet of Things. You can, say, control your freezer or your TV or your toaster remotely over the Internet. So it makes sense to be concerned about security here. You come here to attend this short course, and someone turns on your toaster when you get back home. Okay. So these are the resources we have available. What do we attain when using code-based cryptography? Our program fits 5.6 kilobytes out of 32 kilobytes, so there is plenty of room for your application, toaster controlling application or that. Out of 8 kilobytes, we use 2.6 kilobytes for our variables. We have essentially to store syndrome and parity check matrix or so. Key generator takes less than 1 second, encoding 25 milliseconds. It's very, very fast. Decoding less than 3 seconds. When we compare this with the expected performance on a PC, it seems slow, but it's less than 3 seconds. If we measure time by what a human user would perceive, it's you press a button, 1, 2, okay, it's decoded. It's like that. So it's acceptable for use under those circumstances. If you implement this on a full-fledged, on a powerful processor, modern processor, then performance is very, very high. You can achieve very high throughput. I don't have the data here, but it's very high. You can split implementation as well, assuming you will only encrypt or only decrypt or do only one of them. So resources, the needed resources are even less than that. The same code would fit an even poorer environment. Although we thought about implementing this on poorer environments, but none of them had a TCP/IP module, so it would not be characteristic of the Internet of Things. So, okay. And, well, that's it. What next? My final slide here. Codes are fine for encryption. That's okay. Codes are not fine for digital signatures, as we saw yesterday. And since they are not good for digital signatures, they are not good for identity-based cryptography. Identity-based cryptography, one way or the other, involves signing something. The private key is computed by an authority by signing a user's identity. If we don't know how to sign efficiently, we cannot do identity-based cryptography using codes. We will have difficulties in doing other things as well, e-voting, e-auctions, or ring sigma. Well, I was trying to find this word, signatures, but everything involves doing signatures. We cannot do signatures efficiently using codes yet. There is another trend, another research trend involving codes, but now dropping the Hamming notion of distance. Drop the Hamming distance. Choose a different metric. It's essentially the same thing that we do when switching between codes and lattices. Lattices use a different notion of distance, a different notion of norm. So do the same, but remaining in the realm of codes. For instance, use the rank metric code. So is it possible to do digital signatures efficient? Yes. The security of rank metric signatures is still very poorly understood, but existing attack techniques don't seem to work. It doesn't mean that there is no technique adapted to rank metrics that will break those schemes. They are less than 2 years old, actually. So it's 2013. This family of crypto systems was proposed, and it looks quite promising because key sizes are about the same as we get here using QC MDBC codes. Signature sizes are roughly the same as well. Processing is not as efficient using naive techniques, so there is an opportunity for doing research, how to improve the algorithms, how to choose codes. The authors were not able to provide a full assessment of how secure those codes are, but there is a growing number of people doing research about this. So it's possible that we will finally solve not only the problem of efficiently computing signatures, but according to one of the leading researchers on this area, he believes that we can do homomorphic encryption using codes as well. People that do research with lattices are probably used to this. A fully homomorphic encryption means that we can essentially compute any arithmetic expression on your ciphertext, and you get a ciphertext corresponding to the result of that operation applied to the plain text. So, sorry, you can maintain your data distributed in the cloud, to use a buzzword, and although it's encrypted, you can compute anything you like. You get the encrypted result and you decrypt locally. So you don't have to reveal any information whatsoever. And it's very hard to do that. It's possible to do it using lattices, but keys are very, very large. It seems to be possible to do the same in the rank metric code, so it's quite possible that this will be a hot topic in the immediate future here for code-based cryptography. And so if we can do even that, it's quite possible that we will finally get blind signatures, which are important for e-voting, digital currencies, auctions, ring signatures, anonymous credentials, things like that, identity-based encryption. So those are some of the subjects that people are tackling right now. And that's, sorry, I pause it. Any more questions? Yes?
The schemes you described are basically useful for public key cryptography.
Yes.
Are there also good schemes for symmetric?
Well, the last slide I presented yesterday reported on the use of codes for constructing hash functions. The trouble is that they are very slow. So, also they are very resource consuming because of the matrix. They have to store matrices. So they will probably not fit a very constrained environment like embedded platform, microcontroller, sensors, and so. There is a proposal for a stream cipher, whose security also is also based on the hardness of syndrome decoding. It's called SYND. It's SYND. It comes from syndrome decoding. It's the same thing. It's quite slow. You obtain something that is very far from being competitive with existing alternatives like cryptographic sponge. It's orders of magnitude faster. So it is possible. You get very strong security properties. So violating the security of this symmetric primitive, which is based on codes, is equivalent to solving a hard problem like syndrome decoding or the like. But the price to pay is that it's very slow, it takes a lot of storage. Yes?
I know that for the physical there are some stopping sets and tracking sets which make the decoding fails, although usually if we change the branching maps, works fine. So, do you know about anyone using this stuff? So,
MDBC codes? Or?
LDBC codes, yeah. I'm not sure if it was
no, sorry, I missed the beginning
so,
of
for instance, the message passing decoder is strongly relates on telegraph or
yes.
But purging might be better for the same code. So like this stopping set and tracking set in the channel. Have you had anything about this use, because you can choose good purging minus or bad one, so like it could be either easy or impossible to decode with this decoding.
I'm not sure I understand it yet, but since you know everything about the messages you are exchanging, you know the exact number of errors you're going to introduce beforehand, you can design your code so that the probability that an error occurs is as low as the probability of an attacker guessing your private key and finding it. If you are satisfied with that probability for security, it's reasonable that you'll be satisfied with that probability of finding an error. You can also filter, as I said. So, I mean, you can ensure that your code will not have loops of with 4 or 6 or it's efficient up to that. There are methods to ensure that your code doesn't have very short loops. But as far as I know, this is all that is being done. There's no existing study of how to generalize it or to see anything different from this. Because it's not like communications where you don't know beforehand how many errors there are, so your code may simply be totally unable to correct errors. So it's a very controlled situation here because of the kind of application you use those codes. If your concern is to correct more errors so that the density would have to be lower, you could use turbo code or so. But here, all we need is we have to be able to correct this number of errors, no more than this, but also no less for security. So I don't think people are doing research about this right now.
This is more like utilizing the literature of physical layer security, what he says, because they do physical layer security, where they just modify coding schemes in a way that, for example, more than one code word is assigned for a specific message, so that these kind of works, I think they are not in the literature of cryptography.
I certainly don't think there is any cryptographer working on this. It's any more questions?